welcome to my talk today. So I will present hidden failure modes in fast charging, what we miss at the cell level. The main idea is simple, very simple. Fast charging is often framed as high currents, high temperatures, and infrastructures challenges. But the fact is, the failures takes in the within the cell. So today my talk will covers the how we are able to probe the different or heterogeneous failure mechanisms uh, occurred during the fast charging at a different fast charging or different fast charge protocols. So today the fast charging is no longer only for EV topics. It has moved to flying taxis, drones, and high energy applications like high energy and high power applications like aviations. So now batteries are powering to these high uh, power density applications devices. And then if you can look at the power density required from EVs to aviations, it is increasing. It requires more power densities. And then the duty complexity also, if you can look at, it is more rigid within the like more tightly safety uh, requirements. But the myth is managing current and temperatures at the pack level. We might think like it will solve the issues, but uh, as we certify the battery packs and different manufacturers' cells, so the failures are born in the cells depends on what kind of stress factors or test conditions we are applying. So today, my talk based on the requirements for EV and other high power density applications. We are considering we started the research on how the SOC or delta SOC, we can say, or SOC DOD function impacts on the cell failure and the cycle life and how it triggers the safety aspects. That's what the main focus. I'm going to provide the informations with our initial experimental results at laboratory tests from the laboratory test, and then if you can look at for this study, what we did was we have chosen the SOC DOD windows from 100 to 80 because we need high energy density also, means the utilization energy density from the cell level should be very high, and 80 to 100 it is like a margin for the electric vehicle applications, or even you can say drones applications. Uh, we used the Taguchi orthogonal test optimization. What we did was we have three different SOCs, three different DOD combinations. With that, we developed the nine test conditions test matrix. Here, nomenclature we can say the T, SOC, and the DOD. I will represent in every slide. So these nine test conditions, again, we categorized into four groups. One is full charge, full discharge is a
Vallabha,
mode, and then full
hello.
charge with the hello.
Vallabha, can you hear us?
Yes.
Uh, are you sharing any slides? Because we're not able to see anything.
Oh, really? Oh,
Yeah,
I'm sorry. Oh, I'm sorry. I'm sorry.
no worries.
I'm sorry. I'm sorry. Oh, can you see?
No,
No.
Still not.
Oh, okay. 1 second. 1 second.
yes, now we can. Yeah.
Oh, my apologies for this inconvenience. I'm sorry.
No.
So today my talk will focus on the hidden failure modes in fast charging. Our main focus is what we missed the aging modes in the cell level itself. So that if we can identify those aging mechanisms or failure modes as a function of what current rate, then we can easily adopt those current rates into the pack level systems. That's the main idea. So as we see here, the fast charging is no more consideration for the EVs. It is actually adapted to high power density applications like flying taxis to drones and aviations. And then these applications, the duty cycles complexities increases because the duty cycles are very shortened. So it will triggers the more safety issues. So that's why we have to consider what kind of aging mechanisms or what kind of failure modes are happening during the initial cell testings and all. So as I mentioned, for this one, we have consider the design of experiments based on the operating SOC and DOD windows. And at fast charging, like fast charging, generally they consider as a 15 minutes of charging uh, uh, to uh, 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 to charge the battery fully within the 15 minutes. So that based on that consideration, we have considered the 4C charge rate for the cells. And then here the test protocols are like the charging and discharging current rates are the same. And then we have not provided any constant voltage charging mode in our system. So, and we have implemented this test matrix based on the Taguchi orthogonal designs. So what we consider was SOC and the DOD is three SOC conditions, 100 SOC, 90 and 80, with the combinations like three DOD conditions, 100, 90 and 80. So based on these combinations, we have derived the 9 test conditions. And then when I'm going to show in the further slides, SOC DOD combinations, I'm representing with the T, SOC, and the DOD kind. This is the nomenclature I will use it. And then these 9 test conditions, again, we categorize it into 4 groups. One is a full charge and a full discharge. Another one is a full charge with the partial discharge. And then partial charge with the partial discharge. And then a partial charge, full discharge. And a partial charge with the partial discharge. So if you can consider any test protocol which has implemented in our EV applications, those test conditions supposed to be comes under these 4 categories, so that it will helps us what kind of aging mechanisms might be occurred or going to happen. So those kind of for getting that information, we designed our experiments in 4 categories. So in full charge, full discharge conditions, so we have only one test condition that 100 SOC charge and 100 depth of discharge. Whereas in the full charge, partial discharge, only two conditions were met. One is 100 SOC, 80 DOD, 100 SOC and 90 DOD. And then whereas in partial charge with the full discharge mode, 80 SOC with 100 DOD and 90 SOC with 100 DOD, means full discharge. Whereas in partial charge, partial discharge mode, we have considered the 4 test conditions. So I'm going to walk through means how these aging mechanisms were involved, whether it is a different because all the charging current rate is the same. Uh, then how the aging mechanisms will be differ as a function of these SOC and the DOD. So the initial test condition we have considered is 100. Oh, here for this entire study, we have chosen the A123 commercial cell, high power cell, and then we have done the tomography analysis to see the internal structure, and then it is clearly visible that it has 4 uh, tabs on the cathode side and 4 tabs on the anode side, so that the current distribution within the jelly roll will be uniform. So which is one like standard model for considering for the study the aging mechanisms. So in a first case, full charge and full discharge condition, we can see the cycle life was limited to 950 cycles, and then the cell temperature rise was increased after onset onset capacity fade onwards. And after onset capacity fade, the capacity fade was accelerated, and then temperature rise was also increased. So we parallelly we probed the cell resistance behavior, and we have used electrochemical impedance spectroscopy. Here we can see over the cycles the EAS spectrum was shifted, the behavior was shifted, means which is saying like the resistance was increased. But interestingly, after 400 cycles, where the onset capacity fade was observed, after the few cycles, the again the cell resistance was reduced. So, which is very strange, and it is repeatable. Even when we check it with the three different, means the three cells repeatedly, the behavior is the same. So the temperature rise and then impedance change behavior won't give any kind of aging mechanism. What kind of aging mechanism was involved in the cell level? But it can gives these two are the symptoms. Like there are changes, the chemistry or the properties or some kind of aging mechanisms were occurred at this particular cycles. That kind of information only we can get it. So to understand further what kind of aging mechanism was involved in this cell at this test condition, we have carried out the X-ray tomography analysis. So this is a non-destructive and in situ characterization, so that we can able to just study or identify where the aging mechanisms or failure mechanisms are occurred. And second thing is, usually we will think the failure modes mostly related to chemical degradations or electrochemical degradations, but mechanical degradations also will actually impact on the cycle life and as well as the safety of the cells. So here we can see in this test condition, um, after end of the life, we can see the lot of gas pockets formations within the jelly roll, and at an interface of the cathode and the separator, we identified some degradation mode also. So it is clearly saying that some kind of heat generation or the electrolyte evaporation mechanisms were occurred. But these two information still not enough to probe what kind of aging mechanisms really involved in this test condition. Um, the general phenomena or general idea from the Patrick group is, when we charge the cell at 100 SOC 100 DOD, the first impression is, oh, we are doing at a full charge. So might be the lithium plating or the SAI layer, solid electrolyte interface layer decomposition behaviors can be observed. But if you can look at the cross section or even the CT scanning images, the jelly roll deformation and gas formations are also impacting on the cell performance. So to further understand why this the gas formation is occurred, or why this interface was degraded, for that we have done the DP analysis. We can see here, after a DPA, even entire roll, the jelly roll, the delamination was occurred more. And then after that, the electrodes were harvested, and then we have carried out the top sims depth profile analysis. Because we want to understand what aging mechanism was really occurred as a function of this test condition. So from the pristine electrode to the aged electrode, end of the life cycle electrode, if you can see, along with the SA layer compositions on anode side, we have identified the Fe, means this is the LiFePO4, the Fe signals we have identified, and as well as on the cathode side, from the surface, some up to some depth of the electrode, the Fe signals were reduced. So these two images or analysis clearly indicates that the iron, which is the transition metal in the cathode, was leached out, and then it has migrated to the electrolyte system and then deposited on the surface of the anode. So now To understand the Fe concentration on the electrode, we have carried out a high resolution TEM analysis. Of course, I'm just walking through in academic a little bit, but in this from this TEM analysis, you can see the few uh, uh, nanometer scale Fe nanocrystals clusters we have identified on the graphite surface, and then and these are like deposited on the surface of the anode layer. Here anode is a graphite, so on the graphite surface. So whether it is fully diffused into the structure of the graphite or on the surface, for that we have done the further analysis. We have done the line mapping of the that area where the Fe particles were identified, and from the line scan analysis, we can see where the Fe particles or clusters are deposited, there the other SA compounds concentration, like the chemical composition was very high, very rich. So which is clearly say indicates that the deposited iron particles from the cathode acts as a catalyst, and it is continuously actually degrading the electrolyte system and then forming the SA layer on the where Fe was deposited. So here two things. One is when Fe is acting as a catalyst, and then the continuous SA solid electrolyte growth is happening by decomposing of the electrolyte. So the byproduct is the gas formation. So whatever we have seen initially in a jelly roll from the CT scan image, the gas pockets are formed due to because of this reason also. And the thing is now how this Fe can be leached out from the cathode. That is a like under like what we can say is unknown phenomena. So then we thought if we can look at the temperature profile, when the temperature rises increases, then what happens is the electrolyte compounds will react with the trace amount of the moisture in the electrolyte system, and then it can generate the protons, and then that protons can actually attack the cathode material when it is in during the charging process, and then the protons can be replaced with iron from the cathode, the transition metal, and then the transition metal will be leached out, and then it can deposit. So here two mechanisms are happened. One is the cell temperature rise, and other one is the continuous formation of the SCA layer. So these two things, how it impacts, what kind of modes has happened in the cell as a function of this test condition. Then we have carried out the Preston and the aged cathode and the anode electrodes we have harvested, and then we have done the initial electrochemical cycles. So from this off cell lithium as a lithium metal is a reference electrode here to understand and probe the amount of the lithium in the active lithium and the dead lithium in the both electrodes. So from this analysis, we identified the LFP contribution, like the mode, for example, inventory loss of lithium ions or active material loss. If you can see from the cathode side, it is more, and whatever the transition metal is leached out and deposited on the graphite. Because of that, the LLI even further increased. The quantity was increased in the graphite side. So one myth was here. Every time we can say the fast charging. During the fast charging or fast charging applications, the anode is a limiting factor, we can say, which is not true always. I can say from our investigations, we can say when the cathode transition metal dissolution occurs, the cathode contribution on the capacity fade or cycle life degradation can be contributed, means the cathode is contributing more. So this is what we understood the uncovered aging mechanism from the cell, for particularly LFP cells for 100 SOC and 100 DOD, full charge and full discharge conditions. Now we thought like, okay, this is a full charge and full discharge condition. So if you can reduce the depth of the discharge, so whether even we are running the same current rates or C rate, so the impact will be the same, or whether the cycle life will be improved or any other aging mechanisms are happens. So for that, we have carried out the full charge and the partial discharge test conditions. Here we can see the charge condition is the same like previous 100 SOC we are going to charge, but the discharge is limited to one case is 80 percentage and another one is 90 percentage of the depth of the discharge. So during the cycle life, the temperature profiles we can see how differs, and which is clearly significant in the obtain the cycle life also. When we have like in the both cases, 80 90 devoted to 80 devoted operation at the same SOC condition, the cycle life was almost 1.2 times or more than one time cycle life was enhanced. And even the behavior of the cell temperature rise at end of the life, if you can see, which is also clearly indicating that the aging mechanisms which are involved in these two conditions are different. So to understand, to probe those aging mechanisms again, we have carried out the similar methodology like the tomography analysis. And from the tomography analysis, if we can clearly observe the 90 DOD condition, the deformation was more, and the deformation is also not actually occurred at an from the like near the tab locations, but we can see it is happened at a center point of the jelly roll. And the we have clearly investigated the origin of this deformation is occurred from the anode side, anode delamination and all. And whereas in the case of 180 test condition, the deformation as well as the gas pocket formations were not identified clearly. But when we have carried out the DP analysis from anode side, if you can see, both the anode for both test conditions are uh, uh, the physical appearance is completely different. In case of 190, we can see clear belt formation of different lithiation phases. We can see outer edge locations at an edge. We can see more active lithium means the graphite phases, whereas in center point, the lithium deposited area was identified. So whereas in the case of 180, we haven't seen any kind of lithium plating or lithium deposition or even the charge gradient formation. So this is one real thing like aging mechanism which was not addressed before. And then we are clearly, we can see here how this DOD is impacting on the anode side and the formation of the charge gradients. Similar way, uh, we wanna look for once you reduce the SOC and then improve means cycle up to full discharge, what kind of aging mechanisms again occurs and how the cycle life will be differs. In our case, for example, 90, 100, depth of discharge is a full 100%, whereas we have modified, it means changed the SOC condition. So this SOC condition actually resulted in almost four times higher cycle number than the 100 SOC and 100 DOD condition, the first conditions. In the first conditions, we got only 940 cycles, whereas in 80 SOC, 100 DOD, the cycle life almost reached the 4,300 cycles. But if you can look at the end of the cycle life, both cell temperature rises the same, and then the impedance behavior was completely different, and it is also indicating that what kind of means how severe aging mechanism was occurred in the case of 90 SOC with the 100 DOD, whereas in the case of 80 SOC 100 DOD, which has given the highest cycle life, the impedance rise is still below the like other test conditions. So further that we try to probe the what kind of aging mechanisms were involved in this case also. And surprisingly, like in a previous case, 100 SOC, 90 DOD, how the anode surface was. Here also a 90 and 100 combination, the aging mechanism on the anode side is similar. So outer like towards the tap sides, the active graphite phases were there, and whereas the middle portion, the lithium deposition and the plating was concentration is very high. And similarly, we have observed the delamination in the jelly roll. It behaves similar like 100 SOC 90 DOD combinations, but the cycle life was a little bit improved, and it is almost similar aging mechanisms. To further investigate, so the hypothesis here and then belief of all industry and battery group is uh, when we reduce the operating SOC DOD window, the cycle life and the safety of the cell will be improved. That is the myth we have. But in our case, if you can see, four test conditions we have studied: 90 SOC, 90 SOC to 90 DOD to 80 SOC to 80 DOD. So 80 SOC, 80 DOD is the lowest operating voltage window of the cell, but the cycle life of 80 SOC 80 DOD is much lower than that of even 80 SOC 90 DOD. So, which is strange, and it is a repeatable, reproducible, I can say. But the cell temperature rise and then the cell impedance, uh, uh, s- uh, like change behavior, is quite different for each test conditions. So, to understand what kind of phasing mechanisms were happened for these four test conditions, again we have done the tomography analysis. Here we can see we have considered 80 SOC 80 DOD and 90 SOC 90 DOD to show even the cell temperature rise was the same, but the internal jelly roll structure was completely changed. The multiple gas pockets I can see like deformations were observed in the case of the lowest operating SOC window of T8080, whereas in the case of 9090 we haven't seen much the deformation in the jelly roll, but whereas near the tabs locations, because the escape, the whatever the gas was formed, it has to escape. So during the escaping process, we can see some deformation at the terminal near the terminal sites. But whereas if you can look at interestingly the anode aging behavior is completely different for all four test conditions. In lowest one, the outer one is more active, inner one is like more lithium plating. Whereas 8090, when we have increased the depth of discharge, the behavior is completely swapped out. It is switched. We can say outer one is inactive and lower means the middle portion was more active. The golden color says like activation of the means what is the lithium phase of the graphite, and the similar we have seen 9080, and then whereas in the case of 9090 it is still like behaves like 90 SOC with 100 DOD, 100 SOC with 90 DOD. All three conditions are the similar behavior. So with this one, I would like to say um, even the like this belt formation is due to because of how the graphite was lithiated and delithiated, which is a strange mechanism. We will assume that the graphite, when we are lithiating or discharging or charging, it will be uniformly the phase formation can occurs. But while after we do done DP and then probed with the Raman mapping, we can see the red color. We can say it is LIC6. The green color indicates the LIC18 lithiation phase, and then the blue one is a pure graphite. So even after end of the discharge at 0% of SOC, the graphite electrode has mixture of different lithiation phases, and based on the islands like the concentration gradients, the cell behavior and then the localized cell temperature rise depends. And another thing is these localized the concentration gradients of the phases also a driving force for the lithium plating, where the current distribution changes, which actually drives the lithium plating mechanism. So the lithium plating and stripping mechanism are occurred more on these three test conditions. That is because of the charge distribution variation. It is not homogeneous lithiation phases on the surface of the graphite at the end of the cell discharge. So with this, I would like to conclude that um, even the C rate is the same, but as a function of different SOC DOD, the aging mechanisms are different. So when we adopt when we derive the fast charging test protocols, well, for example, multi-pulse test conditions and all with a different amplitude of the currents. So based on our investigations, we can say up to 80 SOC, whatever current we can provide, 80 SOC, the cell is not going to be degrade much. But ultimately, when the cell is going to be fully charged at the full SOC condition, the current rate is supposed to be low. Then what happens is your charge gradients um, uh, homogeneity we will obtain, so that the cycle life will be enhanced as well as the cell temperature rise is going to be reduced. So further, I would like to just to finish in a few seconds. So we have further taken these different SOC DOD conditions uh, and their cycle life, and then we put it in a physical models, like surface response models, because we have only studied 9 test conditions, but we can make many combinations from 80 to 100, and each combination, what kind of cycle life it can result in, so that we can identify from this surface model theory. And then we can see here these 9 test conditions. So we use it as a norms for the determine the cycle life as a function of SOC and the DOD, and then ultimately whether the SOC is impacting on the cycle life and safety, or DOD, the depth of discharge is impacting on the safety or cycle life, or the combination of SOC and the DOD is impacting on the cycle life and safety, which we have clearly figured it out from these 9 test conditions. And then using this Taguchi test analysis, from this analysis, we can say SOC is much impact than DOD, and then SOC and the DOD combination is more impact on the cycle life and the safety of the lithium cell. So with this one, I would like to thank you all uh, for attending my talk today. Yeah, if you have any questions, I would like to take, and I would like to thank my mentors, leaders from Fuel Research Institute, and then my previous company uh, leaders. Yeah, thank you.